We left off part 1 of this module on radiation exchange between opaque, diffuse and grey surfaces that allows us to use Kirchhoff's law. The reflectivity is equal to the emissivity of the surface. Then surface radiative resistance was introduced. We are going to see another type of resistance associated with radiation exchange, the space resistance. So let's consider two surfaces, I and J. The net heat transfer from I to J is given by 1328. So we are focusing on surface I. So this is the net radiosity, the radiation leaving due to radiosity from surface I. Subtract that from radiation coming from surface J. Now, if we apply the reciprocity relation, we are going to use this often, it will yield 1329. Now, if you arrange 1329, you are going to get something of this form, which gives us space resistance, where the numerator is just the potential difference. Yeah. So here is a schematic diagram of the electrical analogy of space resistance to radiation. Note that we have here the surface resistance associated with surface I, and here the surface resistance associated with surface J, and between them we have the space resistance. That is for two surface radiation exchange. Next, we consider n surfaces in an enclosure. The conservation of energy requires that the net heat transfer from surface I be equal to the sum of the net heat transfers from surface I to each of the n surfaces. So we consider each of the n surfaces, the radiation exchange. This is from surface I to each of the n surfaces, and this is from each of the n surfaces to surface I. I've marked this with the red asterisk because I'm going to refer to it later. To carefully understand, because it's hard to imagine these I's and the J's, yeah? So let's have a look at a simple three surface exchange. Yeah? So you have here the net radiation leaving surface I is given by this term. Yeah? So this is leaving surface I to surface 1, and this is leaving surface I to surface 2. And subtract that from that, the radiation coming from surface 1 intercepted by surface I, as well as radiation coming from surface 2 intercepted by surface I. So if you use the reciprocity rule, the asterisk equation may be rewritten in this form and rearranged to get 1332 in your e-book. So this gives us the net rate of heat transfer from surface I, which is Q dot I, equal to the sum of components from surface I to each of the surfaces J related to radiative exchange. Now, if you combine 1325 earlier and 1322, this is 1325, yeah, you get 1333, which represents a radiation balance for the radiosity node associated with surface I. It's better described schematically here. So this is the node of surface I. Yeah. So the net radiation transfer current flow, yeah, to surface I through its surface resistance must equal the net rate of radiation transfer current flows from I to all the other surfaces. Yeah. So for surfaces exchanging radiation where they are all black, 1332 reduces to just this, because you have only emission. There is no reflection. So radiosity is just emission. Now, so please note that when you're doing heat transfer analysis for radiation exchange, there are two resistance in radiation exchange. One is the surface resistance, and two is the space resistance. For surfaces with specified heat transfer rates, 1332 may be used. Yeah, actually, this equation labeled 1334 is 1332. Yes. For surfaces with specified temperatures, 1333 may be used. Again, 1335 is just 1333, repeated here. If the radiosities of surfaces in an enclosure is known, 1334 is used to obtain the unknown Q. So you can get Q if you know the radiosities. Yeah. 1335 is used to get the unknown surface temperature. Yeah. If you have the radiosity, you can get the temperature. Now note that we have assumed positive heat transfer from surface I. See, it indicates that it is from surface I to other surfaces. So if you get a negative value, that means the direction is the opposite. Next, the two surface enclosure. The simplest example of an enclosure is one involving two surfaces. Again, we assume diffuse, gray, opaque, which will allow us to use the Kirchhoff's law. So two surface resistance and one space resistance must be considered here. So two surfaces, so we have the first is surface resistance associated with the first surface, and then we have the surface resistance associated with the second surface, and there's a space resistance between them. So at steady state, we have 1336. All the total resistance, this is in terms of the equivalent thermal resistance network, as you did in chapter 3 of your ebook. So it's in watt, and temperature is in Kelvin. So now table 13.3 lists heat transfer relations for some familiar two enclosure arrangements. You have the small object in a large cavity, infinitely large parallel plates. We often see this in engineering devices, infinitely long concentric cylinders and concentric spheres. If we extend the two surface enclosures to the three surface enclosures, it looks difficult, but if you look at each node carefully, in this case we have surfaces 1, 2 and 3. They each have an area A1, A2 and 3, emissivity epsilon 1, epsilon 2, epsilon 3, and uniform temperatures T1, T2 and T3. So each surface has its own surface resistance and the space resistance between itself and the surface receiving radiation from it. So we look at surface 1 here for these three surface enclosures. It has with it the surface resistance, and because it is interacting heat transfer exchange with surface 2 as well as surface 3, it has with it the space resistance. If you look at node 2, that is surface 2, same goes. It has its own surface resistance and the space resistance. So the net radiation heat transfer at each node is 0. So at each node, the net is 0. What comes in must equal to what comes out. So what comes in into this node is the surface resistance, and what comes out are the surface resistance. So we have here three equations with three unknowns. Actually, you can solve this. You can solve for J1, J2, and J3 if you know the other parameters in the equation. You can solve them simultaneously or or a simple code in MATLAB. If one of the surfaces is black or re-radiating, then the radiosity is simplified into just black body radiation. There is no reflected irradiation. Basically, they're all emission. So you use Stefan-Boltzmann equation. Now, if the radiation leaving surface I is known instead of the temperature, then you may replace the term with a known Q. Radiation shields. The net radiation transfer between two surfaces can be reduced by using radiation shields constructed from low emissivity or high reflectivity materials. So it's schematically shown here. Placing a radiation shield, we call it surface 3, between two large parallel plates. Look at the associated resistances with each surface and between them. Without the radiation shield, the net radiation transfer between surfaces 1 and 2, infinitely large parallel plates, is given in table 13.3, equation 13.38. So it's given here. And because they are infinitely large parallel plates, A1 is equal to A2, which is just A. So you have this equation for radiation exchange between surface 1 to surface 2, no shield. With a radiation shield, additional resistances are present and the heat transfer rate is reduced. There are 6 equivalent resistances between surface 1 to surface 2 with the shield as surface 3. So here we have surface resistance associated with surface 1, surface resistance associated with surface 3, but it's facing, there are two surfaces here, one facing surface 2 and the other facing surface 1. So you have two surface resistances here, and you have associated with the interaction of the surfaces, the space resistance. Okay. So we have here equation given the heat transfer, the net heat transfer leaving surface 1 to surface 2 with the shield in place. Okay. Then simply knowing, using the simply knowing that because they are parallel, so the fraction of radiation leaving surface 1 being intercepted by surface 3 is the same as that leaving surface 3 intercepted by surface 2. They're just unity. They don't go anywhere else. Yeah? And with equal areas, you get 1343. Note that this marked yellow term, the denominator, is the resistance due to the shield. The emissivity of one side of the shield, epsilon 31, may differ from that associated with the opposite side. So you do not assume that from the beginning unless it is stated it is of the same material, both surfaces of the shield. So the radiosities will differ if the emissivity on both sides of the shield are different. The resistances of the radiation shield become very large when the emissivities are very small. Now, with N shields, the 1343 may be extended. So you have here one shield, and if the emissivities are equal, it can be simplified into 1345 with N shield, all of them of equal emissivities. So one shield reduces the heat transfer by half, 9 shields reduces the heat transfer by 1/10, 19 shields reduce the heat transfer by 1/20, which is 5% of what it was without any shield. So that wraps up the coverage for chapter 13 of your ebook.